November 12, 1889, Woodstock, Ontario. The engineering assessment from Toronto-trained mechanical consultants would never fully capture what they witnessed that cold morning at the Cowan Foundry. A massive cast-iron contraption being installed using assembly methods that defied everything modern industrial efficiency demanded. Through the machinery noise and iron dust of the foundry floor, James Cowan supervised the final positioning of equipment that seemed laughably primitive to visiting engineers. No compact design, no modern valve systems, no proven track record of continuous industrial operation. Yet he envisioned reliable air delivery that the temperamental belt-driven blowers plaguing Canadian foundries could not match. In established foundries across Ontario and Michigan, companies accepted blower failures as unchangeable reality. Modern equipment broke down weekly, requiring constant maintenance, replacement parts shipped from distant manufacturers, and expensive downtime that disrupted melting schedules. Most carried operational costs that made long-term profitability nearly impossible. The Cowan operation was implementing mechanical philosophy the modernists had dismissed as obsolete. Oversized components, pump-driven airflow, systematic over-engineering of every bearing surface and cylinder wall, cooling methods that reduce stress through patience rather than forced ventilation. In a region obsessed with compact efficiency, the most decisive industrial revolution in foundry equipment history was revealing itself. Not in superior metallurgy, not in innovative valve designs, but in the systematic simplicity that eliminated every failure point modern engineers had introduced while chasing theoretical improvements. James Cowan stood beside that massive blower that November morning, watching his foundry workers puzzle over installation instructions that seemed absurdly straightforward. At 42, he had spent 2 decades building Cowan Foundry into one of Ontario's most reliable producers of agricultural equipment and industrial castings. But the mathematics of survival had become brutally clear. Belt-driven blowers failing every 6 months weren't just maintenance headaches. They were production disasters that could shut down cupola furnaces mid-melt, ruining entire batches of iron and costing more than the equipment itself. Every replacement blower purchased from American manufacturers in Detroit or Cleveland came with promises of improved efficiency and reduced maintenance. Yet each lasted barely longer than its predecessor before bearings seized, belts snapped, or housings cracked under thermal stress that manufacturers hadn't adequately tested. The specifications for this new blower had arrived from Allis-Chalmers through unusual channels. George Patterson, Cowan's master pattern maker, had seen similar equipment operating at a Pittsburgh foundry during a recruiting trip. The American foundry had installed the blower as temporary equipment while awaiting delivery of modern machinery, then discovered their temporary solution outperformed every replacement they tested. Toronto mechanical engineers scoffed when word leaked of Cowan's purchase decision. Installing a blower design that emphasized massive cast-iron construction over compact efficiency violated every principle of modern industrial equipment management. They argued that belt-driven systems offered superior control, easier maintenance access, and proven performance in foundries across North America. Why adopt outdated technology when superior alternatives existed? But Cowan saw what his competitors missed. Standing in his foundry office reviewing Patterson's installation drawings, he wasn't calculating maintenance schedules or efficiency percentages. He was engineering for permanence, a blower that could operate continuously without the bearing failures that plagued modern equipment. No belt adjustments, no complex valve timing, no components too delicate for foundry environments where iron dust and thermal cycling destroyed precision machinery. The pump-driven airflow system used water cooling that prevented the overheating failures endemic to belt-driven designs. Massive bearings, 4 times larger than modern specifications, distributed loads across surface areas that would never wear through even under continuous operation. Oversized cylinders moved air through volume rather than pressure, eliminating the stress concentrations that cracked modern blower housings. Patterson supervised the installation with methodical precision learned through 30 years of foundry equipment maintenance. The German-trained pattern maker had seen every blower design fail, watched countless improvements create new problems while solving old ones. Now he studied the Allis-Chalmers design with appreciation for engineering that prioritized function over fashion. The foundry floor offered everything modern efficiency experts said was wasted space. The blower occupied nearly 300 square feet that could have housed compact modern equipment. Its massive flywheel alone weighed more than complete belt-driven systems. Installation required foundation work that cost twice what modern mounting systems demanded. Within 48 hours, the blower was positioned and connected to Cowan Foundry's cupola furnace through cast iron ducting that would remain unchanged for the next century. Within 72 hours, the first test runs revealed capabilities that would redefine industrial equipment longevity. Modern engineers read the installation reports with mixture of curiosity and dismissive certainty that such crude equipment couldn't compete with contemporary designs. December 1889 through March 1890. The blower's early operation generated more skepticism than confidence among foundry equipment suppliers watching Cowan's experiment. Regional sales representatives from modern blower manufacturers visited Woodstock with technical literature proving their compact designs superior in every measurable specification except the one that ultimately mattered: operational longevity. Charles Henderson arrived from Detroit's Morrison Foundry Equipment Company carrying performance data that made the Allis-Chalmers installation appear hopelessly obsolete. His belt-driven blowers moved 20% more air using half the floor space, while consuming 15% less power during peak operation. The sales pitch emphasized efficiency metrics that impressed purchasing managers focused on initial costs rather than lifetime operational expenses. Cowan listened politely while Henderson demonstrated how modern blower designs incorporated ball bearings that reduced friction, adjustable belt systems that optimized power transmission, and compact housings that simplified installation. Every feature represented genuine engineering advancement that made the massive cast iron blower seem like agricultural equipment in an industrial age. But Henderson's presentation carefully avoided discussing replacement intervals, bearing life expectancy or maintenance costs that would accumulate over decades of operation. His company's blowers carried 2-year warranties because they rarely survived longer. Foundries purchased new equipment every 3 to 5 years as routine capital expense, accepting perpetual replacement cycles as inevitable business costs. Regional foundry operators who visited Cowan's facility expressed polite bewilderment at the blower's crude appearance. William McIntosh from Guelph Ironworks examined the exposed crankshaft and massive connecting rods with undisguised skepticism. His foundry used modern enclosed systems where moving parts operated invisibly within protective housings that collected lubricating oil and prevented contamination. The Allis-Chalmers design exposed every mechanical component to foundry dust and temperature extremes that McIntosh argued would accelerate wear and require constant cleaning. Cowan's installation lacked the protective features that modern equipment specifications demanded, appearing more like steam engine components adapted for air delivery than purpose-designed industrial blowers. Hamilton Steel Castings declined to adopt similar equipment after their chief engineer reviewed installation photographs. Thomas Brennan wrote detailed assessments explaining how the oversized components wasted material, the pump-driven system introduced unnecessary complexity, and the water cooling requirements would freeze during Canadian winters, causing catastrophic damage that modern air-cooled designs avoided. Brennan's technical objections reflected consensus among Ontario's foundry engineering community. Modern blower designs had evolved beyond crude 19th-century approaches through systematic refinement of bearing systems, power transmission methods, and housing configurations. Adopting outdated technology represented industrial regression rather than innovation. American foundry equipment manufacturers viewed the Allis-Chalmers design as marketing failure rather than engineering achievement. Their catalogs featured compact blowers with published efficiency ratings that educational institutions used for teaching modern mechanical principles. Engineering students learned to calculate power consumption, airflow optimization, and maintenance scheduling using equipment that represented current industrial standards. The massive blower operating in Woodstock became cautionary example rather than inspiration. Trade publications mentioned Cowan Foundry's installation in articles discussing how smaller operations sometimes made economically questionable equipment decisions due to limited technical expertise or budget constraints that prevented purchasing modern machinery. January 1890 brought the first significant operational test when temperatures dropped to -25 Fahrenheit, and every foundry in Ontario faced equipment failures. Belt-driven blowers throughout the region seized as lubricating oils thickened beyond pumping capacity. Foundries scrambled to maintain production using manual bellows and temporary steam-driven air supplies that barely sustained cupola operations. Cowan Foundry's blower continued operating without modification or intervention. The water cooling system that critics had identified as winter vulnerability proved remarkably resistant to freezing because continuous operation maintained temperatures above critical thresholds. While competitors dealt with frozen bearings and cracked housings, Cowan's cupola furnace received steady airflow that maintained melting schedules without interruption. McIntosh visited Woodstock in February after his modern blower required complete bearing replacement following the cold snap. He found Cowan's primitive-looking machine operating exactly as it had during autumn installation, its exposed components showing no signs of thermal damage or mechanical stress despite weeks of extreme temperature cycling. The psychological impact among foundry equipment suppliers proved more significant than any operational data. If crude 19th century designs could outperform modern engineering during stress conditions, perhaps efficiency metrics and compact construction mattered less than advocates claimed. Perhaps longevity and reliability represented more valuable specifications than contemporary equipment catalogs acknowledged. But changing industrial consensus required more than single-season performance. Modern equipment manufacturers had decades of institutional momentum, established dealer networks, and engineering education systems that validated their design philosophies. One successful winter didn't overturn prevailing wisdom about mechanical efficiency and industrial equipment evolution. March 1890 through December 1895. The blower's first 5 years of operation revealed patterns that would define its century-long service life. Where modern equipment failed through complexity, the Allis-Chalmers design persisted through mechanical fundamentals that eliminated failure modes rather than managing them. Spring 1891 brought Cowan Foundry's first major production surge when agricultural equipment orders doubled due to Western settlement expansion. Cupola operations increased from 8-hour shifts to continuous 20-hour melting cycles that pushed every piece of foundry equipment beyond design specifications. Modern foundries responded by installing additional blower capacity, rotating equipment to prevent overheating, and scheduling mandatory maintenance windows that interrupted production schedules. Cowan's single blower absorbed the increased demand without modification or rest periods, its oversized components distributing loads across bearing surfaces that showed minimal wear after 18 months of operation. The pump-driven airflow system demonstrated unexpected advantages during extended operations, where belt-driven blowers required constant tension adjustments as leather belts stretched under continuous use. The water-cooled pump mechanism maintained consistent delivery pressure through mechanical linkages that didn't degrade. No belts to replace, no tension to monitor, no gradual performance decline as components aged. George Patterson conducted his first comprehensive maintenance inspection in October 1891 after 2 years of service. He found bearing surfaces that appeared barely used despite moving thousands of tons of air through the cupola furnace. The massive cast iron components that critics had dismissed as wasteful over-engineering now revealed their purpose, distributing mechanical stress across surface areas so large that individual contact points never experienced pressures sufficient to cause measurable wear. December 1892 brought catastrophic failure to Hamilton steel castings when their modern Sturtevant blower suffered housing crack during peak production. The failure cascaded through their operation, shutting down cupola furnaces mid-melt and ruining 3 tons of molten iron. Replacement equipment required 6 weeks for delivery from Massachusetts, forcing Hamilton to subcontract production to competitors while paying for idle workforce. Thomas Brennan visited Woodstock during Hamilton's shutdown, examining Cowan's blower with new appreciation for design philosophy he had previously dismissed. The machine that looked primitive now appeared deliberately engineered for permanence rather than efficiency. Every component oversized, not through ignorance but through understanding that generous proportions prevented the stress concentrations causing modern equipment failures. The water cooling system that Brennan had criticized as freeze-vulnerable proved remarkably robust through 3 Canadian winters. Continuous operation maintained internal temperatures that prevented ice formation, while the thermal mass of cast iron Components stabilized temperature fluctuations that caused rapid cycling damage in modern air-cooled designs. Guelph Ironworks experienced similar equipment crisis in 1893 when bearing failure destroyed their Morrison belt-driven blower during autumn production season. William McIntosh calculated replacement costs exceeding original purchase price when accounting for lost production, emergency equipment rental, and accelerated delivery charges that suppliers demanded for rush orders. McIntosh's subsequent visit to Cowan Foundry focused less on technical specifications than operational economics. The massive blower's initial cost had exceeded modern alternatives by 40%, but 3 years of zero-maintenance operation had already generated savings that would compound annually for decades. Every bearing replacement, belt adjustment, and maintenance shutdown that plagued modern equipment represented costs the Allis-Chalmers design simply didn't incur. By 1895, 6 Ontario foundries had installed similar blowers despite continued skepticism from equipment suppliers emphasizing efficiency over longevity. The installations created an informal network of foundry operators who shared maintenance experiences and operational data that contradicted prevailing wisdom about industrial equipment management. These early adopters discovered patterns that would characterize blower performance for the next century. The machines required essentially zero maintenance beyond periodic lubrication, using procedures so simple that foundry laborers handled them without specialized training. No bearing adjustments, no alignment checks, no replacement parts inventory, no maintenance windows interrupting production schedules. The exposed mechanical components that modern engineers had criticized as contamination vulnerable proved remarkably tolerant of foundry environments. Iron dust that destroyed precision bearings in enclosed systems simply fell away from the massive bearing surfaces without causing measurable wear. Temperature extremes that warped modern housings barely affected cast iron's components, with thermal mass sufficient to absorb cycling without dimensional changes. Patterson documented performance data that challenged fundamental assumptions about industrial equipment evolution. The blower's power consumption remained constant, while modern equipment showed gradual efficiency decline as components wore. Airflow delivery maintained specifications, while belt-driven systems required regular adjustments to compensate for mechanical degradation. Most significantly, the blower showed no signs of approaching end-of-service life. After 5 years of continuous operation under conditions that consumed modern equipment in months, Cowan's installation appeared capable of indefinite service. The massive components that seemed wasteful during installation now represented investment in permanence that modern efficiency calculations hadn't valued. January 18, 1896 through December 1910. The blower's second decade of operation revealed engineering principles that contemporary mechanical theory had dismissed as obsolete. What critics had interpreted as primitive construction actually represented sophisticated understanding of how materials behaved under sustained mechanical stress. Professor Edmund Morrison from University of Toronto's Mechanical Engineering Department visited Cowan Foundry in 1897, seeking to understand why outdated designs outperformed modern equipment his students studied. His examination revealed design philosophy fundamentally different from efficiency-focused contemporary engineering. Modern blower manufacturers optimized for power consumption, calculating precise bearing dimensions that minimized friction while meeting expected service intervals. Their designs worked beautifully within theoretical parameters, failing only when real-world conditions exceeded carefully constrained assumptions about operating environments, maintenance schedules, and usage patterns. The Allis-Chalmers approach eliminated optimization entirely. Instead of calculating minimum bearing dimensions, designers specified components 4 times larger than stress analysis required. Rather than selecting materials for theoretical efficiency, they chose cast iron for its capacity to absorb abuse without catastrophic failure. Where modern engineering pursued precision, this design embraced generous tolerance. Morrison's technical assessment identified specific engineering decisions that created unexpected longevity. The massive flywheel that seemed wastefully heavy actually stabilized rotational speed during cupola demand fluctuations, preventing the cyclical stress loading that fatigued modern crankshafts. Oversized connecting rods distributed forces across bearing surfaces so gradually that contact pressures never exceeded levels causing measurable wear. The pump-driven airflow system incorporated principles that wouldn't appear in mechanical engineering textbooks for another 50 years. By using water displacement rather than mechanical compression, the design avoided pressure spikes that destroyed modern blower housings. Water's incompressibility created smooth force transmission that eliminated the hammering loads generated by belt-driven systems. Water cooling served multiple functions that contemporary engineers hadn't recognized. Beyond preventing thermal damage, the continuous water flow carried away microscopic wear particles before they could act as abrasives between moving surfaces. The cooling system essentially flushed contamination from bearing surfaces automatically, maintaining lubrication effectiveness without manual intervention. The exposed mechanical components that modernists criticized actually extended service life through accessibility that enabled observation without disassembly. Foundry workers could visually monitor bearing condition, detect lubrication problems, and identify potential issues, while equipment remained operational. Modern enclosed systems hid developing problems until catastrophic failure forced emergency shutdowns. By 1900, Cowan's blower had operated continuously for 11 years without requiring replacement parts. Contemporary equipment from Morrison, Sturtevant, and other leading manufacturers averaged 18 months between major maintenance events. The cost differential had become mathematically undeniable. Primitive design eliminated expenses that modern efficiency created. Regional foundries began requesting similar installations despite resistance from equipment suppliers whose business models depended on replacement sales and maintenance contracts. Canadian Blower Company of Windsor, Ontario, started manufacturing domestic versions using Alice Chalmers principles, creating competition that challenged American manufacturers' dominance. The 1903 Ontario Foundrymen's Association Conference featured presentations comparing long-term operational costs across different blower designs. Data from 20 foundries demonstrated that massive cast-iron blowers averaged 97% uptime over 5-year periods, while modern compact designs achieved 63% availability after accounting for maintenance shutdowns and replacement delays. James Cowan addressed the conference explaining how design philosophy affected equipment longevity. Modern engineers calculate what components must do. These old designs considered what components must survive. The difference determines whether machinery lasts months or generations. His comments reflected growing recognition that optimization for efficiency often created optimization for failure. By pushing components to theoretical limits, modern designs eliminated safety margins that absorbed unexpected stresses. Equipment performed beautifully under ideal conditions while becoming fragile when reality diverged from assumptions. The blower's success inspired similar approach in other foundry equipment. Pattern shops began designing flask-handling equipment with generous proportions that sacrificed compactness for durability. Cupola charging systems adopted simpler mechanisms that required less maintenance than sophisticated automated alternatives. By 1910, the industrial consensus about foundry equipment had shifted dramatically. What began as isolated experiment in Woodstock, Ontario, had demonstrated that 19th-century engineering principles produced 21st-century longevity. The blower that critics had mocked as crude and inefficient had operated flawlessly for 21 years, while consuming 3 generations of superior replacements. Patterson's maintenance logs recorded the complete history: routine lubrication every 3 months, bearing inspection annually, 0 component replacements, 0 unscheduled downtime. The economic advantage had become overwhelming. Cowan Foundry's blower investment had paid for itself within 5 years, then generated 2 decades of essentially free air delivery while competitors continuously purchased replacement equipment, January 1911 through December 1945. The blower's middle decades coincided with industrial transformation that should have rendered it obsolete. Electric motors replaced steam power, pneumatic controls superseded mechanical linkages, and precision manufacturing enabled compact designs impossible during the 1880s. Yet the ancient cast-iron machine continued operating while technological progress created new failure modes: World War I production demands tested every foundry in North America. Cowan Foundry received government contracts for artillery shell casings requiring continuous cupola operations that pushed equipment beyond peacetime specifications. Modern foundries installed additional blower capacity to handle increased air volume demands, creating redundant systems that prevented single-point failures during critical war production. Cowan's response involved no equipment changes whatsoever. The 1889 blower absorbed doubled air delivery requirements without modification, its oversized components finally operating closer to original design capacity. 24-hour operations that destroyed modern equipment barely stressed the massive cast-iron construction that had been over-engineered for precisely such contingencies. Military inspectors visiting foundries throughout Ontario documented equipment reliability as part of production capability assessments. Their reports noted Cowan's blower as anomaly, equipment predating most foundry workers still operating at specification, while contemporary machinery required constant maintenance to sustain war production schedules. The 1920s brought electrification that revolutionized industrial equipment design. Electric motors enabled compact blower configurations impossible with belt-driven systems, creating new generation of equipment that promised superior efficiency and reduced maintenance. Foundry equipment suppliers marketed electric blowers as modern solutions that rendered old-fashioned designs obsolete. Cowan Foundry installed electric lighting, electric cranes, and electric welding equipment while leaving their 1889 blower mechanically unchanged. The contrast became increasingly stark as decades passed, contemporary technology surrounding ancient machinery that somehow outperformed everything meant to replace it. George Patterson retired in 1928 after supervising the blower for 39 years. His replacement, Robert McLeod, received maintenance logs showing bearing inspections, lubrication schedules, and operational notes spanning 4 decades. The mechanical condition reports read identically year after year. Minimal wear, continued specification performance, no component degradation. McLeod's engineering training emphasized modern equipment management, predictive maintenance, and systematic component replacement before failure occurrence. The blower violated every principle he had learned. Its maintenance consisted entirely of lubrication and observation, with no scheduled component replacements because nothing wore out sufficiently to justify replacement. The Great Depression eliminated most Ontario foundries as construction markets collapsed and manufacturing demand disappeared. Companies operating modern equipment faced bankruptcy when maintenance costs continued during periods of minimal revenue. Foundries couldn't afford replacing worn blowers while simultaneously managing reduced sales and struggling to maintain workforce. Cowan Foundry survived partly through diversified markets, but significantly through equipment that required essentially zero capital investment during economic crisis. The 1889 blower continued delivering air whether foundry operations ran 8 hours weekly or 80 hours, its operational costs limited to lubricating oil that cost pennies per month. By 1935, the blower had operated 46 years while consuming 0 replacement parts. Contemporary equipment from the 1920s was already approaching end-of-service life, requiring major rebuilds or complete replacement. The economic advantage had become generational, one installation outlasting 3 complete equipment cycles at competing foundries. World War II,